So now we're going to discuss about the Fourier transform. Now, previously we reviewed the Fourier series, which allows us to kind of deconstruct a periodic function using a sum of sines and cosines. Here, we're going to be talking about the Fourier transform, which is similar, but for the case of continuous functions in general. So the definite so Fourier, just to kind of give you an idea, is a special case of Laplace. So let's first introduce the Laplace. The Laplace on a function f of t is the complex frequency representation given by the integral from negative infinity to infinity of f of t e to the negative s of t dt. In this, S was equal to sigma plus j omega. Or if this is maybe perhaps confusing notation, a plus bi. It's a sum of real and imaginary parts. Now, for the situation involving Fourier, it is a special case of Laplace where sigma is equal to 0. So in the event that we see that sigma is equal to 0, we have something called a Fourier transform. Very similar to Laplace, except only for the imaginary part. So let's take a look. So the Fourier, the notation for it is this fancy f acting on some kind of function f of t, which transforms it from a time function to a function of complex frequency, or rather I should say imaginary frequency. Now, the definition for this is the integral from negative infinity to infinity of f of t e to the negative j omega t dt. So if we compare forms, we can see that this and this can be transformed into one another if we let sigma equal 0, or if we let a equal 0. So now, that's the idea of Fourier transforms. But why would we want to care about Fourier transforms? Well, just in general, whenever you are wanting to talk about something in terms of its frequency domain, it would be preferable to talk about it when we're talking about its frequency content. Laplace does not really reflect frequency content. More so, it reflects in general the complex frequency content. This one represents more closely our frequency content, so we're able to kind of discuss about it a little further. So that is simply the Fourier transform. Now, notice that based on this is very similar to Laplace. If we're able to find a valid Laplace transform that acts on some kind of time function f of t, we're able to say that that has a valid Fourier transform. However, the conditions vary a lot. We can't use exponential order like we did with Laplace transform, and certainly we can't use racing it to our advantage. Because the idea is, what are we really, saying if we say e to the j infinity? Like, well, what does that mean? So we can't really say that all functions are going to be, necessarily defined. However, it turns out that we don't really need to care about that because our scope of Fourier transforms are actually very limited. And luckily it is good for our case because we don't have to talk too much about needing to care about the cases that are diverging. For example, It used to be that u of t would have transformed into 1 over s. However, if we apply the Fourier transform onto u of t, we can see that we're asking what's the area underneath this curve? I mean, there is no fixed area underneath this curve. It keeps going on forever. So in this case, the step function technically dominates. So, I mean, why then should we care about Fourier transforms? Well, because when it comes to communication systems, assessing its frequency content allows us to do modulation. And we'll talk about modulation when it comes to application later on. For now, there are just only a handful of Fourier transforms that we care of. Sine, let's say, of 2 pi fct, cosine 2 pi fct, e to the j 2 pi fct, and delta of t minus t naught, as well as just its representation in the, there's a representation of its transformation in the frequency domain. These are the ones that we will care about, and we'll explore those properties a little further. Actually, I would put this too, just to keep it more generalized. Okay, so we'll explore these in a little more detail in the next video. All right, thank you.